Good afternoon. We're about to start the last session of today. So we're going to have two talks of formal verification of systems. First, I'm going to present Agustin, who's going to present a work on verifying Android's permission model.
Well, thank you for the introduction. Good afternoon to everyone. Today I'm going to talk about the paper I've written with Carlos Luna, Juan Campo, and Gustavo Betarte, whose title is Verifying Android's Permission Model. Well, as the title says, what we did in this paper is to write a formal specification of the Android Lollipop security system. And then we prove some security properties on that specification using the code proof assistant. Well, for those who are not familiar with COG, this is a tool that works within the calculus of inductive constructions, and it allows to write formulas and definition of that theory, and it also provides a theorem prover to prove them interactively. All right. Once you prove something with code, you got a sort of guarantee that the correct steps were taken in the proof. I'm going to describe the specification we made, but before I wanted to give you a brief introduction of the Android concept which are involved in the specifications, so that we all know what is being represented. Cool, so let's begin with the introduction. As you all may know, Android is an operating system which was originally designed for mobile devices, and it has been developed by Google and the Open Concept Alliance. This operating system is implemented on top of a multi-user Linux operating system in such a way that, at least by default, each application running on Android is assigned a different Linux user identification. One of the key aspects of the Android design is that any application can invoke another application services. This allows that the application does not need to implement services or functionalities that are already implemented by another application present in the system. Well, talking about applications, these are built by combining 4 types of components. Each kind of component has a specific functionality in the application's lifecycle. Well, the 4 kinds of components of application components are activities, content providers, services, and broadcast receivers. The activities deal with the user interaction. Each activity specifies a screen that the application will have. For example, the inbox screen of an email manager application. The content providers act as interfaces between the data that wants to be shared by an application and the external applications. in such a way that if a foreign application wants to access some particular data of an application, then it must do it through a content provider. Well, the other two kind of components won't be explained with great detail in this talk because they weren't deeply studied in the paper. Well, the communication between applications is in fact done between the application's individual components, not between the entire application themselves. In the case of activities, broadcast receivers and services, they communicate each other using an asynchronous message called intent. When an activity receives an intent, first it processes the information that might come inside that message, and then it fires its corresponding screen. For example, here I show very schematically, of course, a web browser activity that is sending an intent to another activity of a different application. In this case, it is the screen, the activity that corresponds to the composed image screen. The result of this is that the user will see the new screen appearing. Well, the communication with content providers is rather different. It is done using either queries, which are written in a very simple query language provided by Android, or using UDIs. The latter mechanism works as follows. If an application wants to share a particular piece of information, then it can assign a UD of the content provider. If an external application wants to access that particular information, then it must specify the appropriate UD that was assigned to it. For example, if an image viewer application wants to access, for example, an attached picture, then it has to specify the corresponding UD. Well, now let's talk about the Android security model. One of the main aspects of this model is that it tries to comply with the so-called principle of least privilege. This principle says that an application should have access to a resource it needs to function and no more. Well, how this is achieved? Well, thanks to two basic aspects. The first one is called application sandbox, and it forces that applications cannot have access to the rest of the system by default. It is locked in its own sandbox. If the application wants to access other application services or the system services, then it must request the appropriate permissions to do so. While these permissions are requested by specifying them in a file, but that must be present in every Android application, which is called Android manifest. This is not more than an XML file in which, apart from specifying the permissions that are to be requested, the Android developer can specify some basic properties that the application will have. Well, when the application is to be installed in the system, the permissions specified in the manifest are requested, and the user or the system, depending on the kind of permission, decides whether to grant those permissions or not. If the permissions are granted, then the installation may proceed, otherwise the installation is aborted. If the application is successfully installed, then it can use the permissions it obtained until the application is uninstalled. Well, however, Android provides an extra mechanism to obtain the appropriate permissions to perform a certain action. This is called permission delegation, and it allows applications to grant permissions among themselves. The main difference between these kind of permissions and the ones I talked to you before is that they can be revoked at random. Well, there are two mechanisms for permission delegations, which are called pending intent and jury permission. The only mechanism we studied in our paper is the latter, so it is the only one I'm going to explain now with some detail. Well, this mechanism is rather simple. Imagine you got an application that has access to a content provider and another application, app 2, which has not. Then the first application can delegate permissions to access to information pointed by URIs 1 and URI 2, for example. After the delegation is done, the application 2 can start accessing the specified URIs until the permissions are revoked. Well, this mechanism delegates permissions in two different ways. We call them temporary delegations and permanent delegations. The main difference is that temporary delegations are performed using URIs. When an activity receives temporary delegations inside an intent, then it first fires its corresponding screen as usual, and then it enables all the components in the application to have access to a specified URIs in the message. Well, these permissions are revoked when the screen fired by the receiving activity ends its execution, or if a method called revoke URI permission is explicitly invoked. The other way of delegating permissions with this mechanism is by permanent delegation, and this is done by invoking a method called grant URI permission. And the only way to revoke this kind of permissions is by executing the revoke URI permission before by any application in the system. Well, now after this introduction, I'm going to talk to you about the general aspects of our specification. As I told you before, it formalizes the Android security model, and the specification was developed in the code-proof assistant. When we were writing this specification, we paid special attention to the permission delegation I explained before, and the interaction between the applications and the system. Well, in a nutshell, our specification is a very simple one, and it is based on finite state machines, in such a way that a system state is defined by several variables. For example, the installed applications, the permission delegation taking place, and several others. Well, this in the code-proof assistant is represented with a record type that consists of several fields that represent these variables. The first field is the one you are seeing here. It's the apps field, which is a predicate that is satisfied if the application that takes as argument is installed in the state being defined. Well, the other two fields, for example, represent the permission delegations taking place, both temporal and permanent delegations. That's why there are two fields. There are other fields representing other variables, but I won't explain them here in this presentation. The other aspects we represented in our model are the actions that make the system change from one state to another. This is represented using the one-step execution relation, which involves two states, the origin and target state, and the action that provoked the state change. More formally, this relation holds if the origin state satisfied all the preconditions imposed by action A to be fired. And if the target state represents the effect produced by by executing action A on the origin state. Well, we represented 10 the actions you are seeing in the slide, and in order to show you an example, I'm going to describe the pre and post conditions of the action read. Well, the post condition is not very interesting. It's just saying that the system state will remain unchanged after the read operation is executed. But the precondition is saying that if the running instance IC would like to wants to access the UDU of content provider CP, then all these conditions must hold. In particular, the last one is saying that the component corresponding to the running instance must have the appropriate permissions to access, to read the UDI, either at install time or by means of a permanent delegation, or by means of a permission delegation, either permanent or temporary. The properties we proved on this specification are quite a lot. Some of them are listed in this slide. Of course, for time constraints, I'm only going to prove the former two. All right. Well, the first one is called access to non-exported content providers, and it describes the following situation. Imagine we've got an application which has a content provider such that in its Android manifest it is specified that the content provider is not exported. According to the Android documentation, this means that this content provider cannot be accessed by any external application. However, we noticed first in our formalism and then in the actual system that if we delegate permissions to access, for example, a UDU or the content provider to an external application, then this external application can create an instance that will be able to access that UDI of the content provider which is not exported. Well, this is formalized in our specification as a lemma. Of course, this is later proved in the in COG. And generally speaking, what our lemma is saying is that if we have a content provider CP which is not exported, that's what the in manifest predicate stands for. And we have a running instance IC which belongs to a different application, then this running instance will be able to read the UDU of the content provider if and only if it has delegated permissions to do so. This lemma generalizes the example I explained you before, and we prove, of course, an analogous lemma for the write operation. Well, the other security property I wanted to describe is called permission redelegation, and it describes the following aspect. Imagine we got an application that has received a permission delegation to access UDU of a content provider ICP. Then this application can redelegate this permission to a new application in such a way that this new application will be able to access the same UDI of the content provider. This provokes that the original application, the one that delegated the permission in the first place, kind of loses control of this delegated permission because it can be indefinitely redelegated by the other application. Well, this is again formalized as a lemma and successfully proved in COG. Perhaps the most important part is the last part, which says that it is sufficient to have either a temporary or a permanent delegation to redelegated, both permanently or temporarily. Alright? Well, in order to sum up, the contributions made by this paper are, well, for a start, an exhaustive formal specification of the Android security system. As far as we know, it is the first formalization made in COG, which represents the permission delegation I explained before, and the interaction between the applications and the system by means of system calls. Finally, thanks to this specification, we were able to prove properties that weren't studied in previous applications, like the first property I've explained, and properties that were already studied in other publications, following each publication its own approach. Thanks to this specification, we were able to prove several properties proved with different approaches under the same formal framework, which is really good for us. Well, as regards to future work, of course, this is the future work is aimed to enrich the model we built, perhaps by representing the delegation mechanism called pending intents, which remains to be represented, or by studying a bit further the semantics of the other component types, like broadcast receivers. And of course, when we finish the future work, there is something we must do, which is represent the changes introduced by the new Android version, which was released one month ago, more or less. The most important change is that the new Android version allows to grant and revoke permissions at runtime. I mean, that is, the user of the system can grant new permissions or revoke the current permissions at runtime. It's not necessary to do it at the start time, and they do not last until the application is installed. Well, although it seems a very big change, our specification was prepared for that because we had news, we knew that this could happen. So the changes shouldn't be a lot. It's just a matter of adding new two actions, and it's not very difficult. Well, I don't know if you have any questions.
Thank you. Thank you, Agustin. So I think we have room for one or two questions, so please.
So, I think the formalization is very impressive, but when you say we verified, I'm not quite sure I understand, what did you verify?
Well, we verified the Android security model representation we built, of course, not the actual system, because the definitions we've used, they all involve propositions and all those kind of elements which cannot be refined in order to get an actual implementation.
But you did not verify that the Android implementation actually meets the specification, did you?
No, we modeled we begin with the Android documentation, which is an informal specification of what the system should do. And with that documentation, we try to formalize it and try to find inconsistencies or something that is not like described in the documentation, like the first security property I probed, for example.
So I would suggest being careful with the word verified, because that's a big claim. and you can say we analyze the security model. But to verify, that means that you actually took the Android code and you verify the Android code meets the specification. And that's a much bigger challenge. And I think that's much more difficult for you to actually do it. And you may want to look at the work done at Microsoft, for example. They look at the interaction between device drivers and the kernel, and which is somewhat related to, I think, what you're doing here. But they actually verified that the device driver satisfies some properties.
Exactly.
The actual code. And there is a tool today. Microsoft, if you're a developer and you build device drivers, you get from Microsoft code, I think it's called STV, Static Device Verifier. And you can check that the code meets the specification.
Well, thanks to this initial work, then we are beginning a new specification with replacing all these predicates that I've shown you before. We chose to use predicate because the specification was more clearer. But then we are going to replace all these things that cannot be refined and try to get an Android prototype and then be closer and closer and closer to the actual implementation. But this, of course, is the initial work, of course.
So, any other question? Okay, actually, I would like to ask a question, Agustin.
Yes.
So, did you manage to find any issues or weaknesses in the security model you analyzed formally?
We've analyzed several properties that were already studied. Of course, they were again improved in our system, and then we focus on inconsistencies of the documentation of the Android security. For example, the property I told you before, the first one. Like misconception that a developer might have that provoke a security issue. Of course, there are other well-known properties that were already proved, like permission escalation and all those aspects all those problems that the Android suffers.
Thank you, Agustin. So let us thank our speaker. So I'm going to introduce Adrian Riesco, who's going to present the second paper of this session. It's on the specification analysis of the Kademlia protocol in Maude.
So thank you very much for the introduction. This is a joint work with Isabel Pita. And Kademlia is a protocol for dealing with distributed hash tables that is widely used in real implementation of peer-to-peer networks because it's relatively simple. As you probably know, there's a lack of security of this kind of tables, so they are mainly used for sharing files, and most of the studies are just performed experimentally. But in the last years, there are more and more formal analysis of these kind of protocols, especially of the short and pass-through DHTs. But for the best of our knowledge, perhaps people think this is too simple, but Kademlia is not formalized. So we present here a distributed specification of the Kademlia protocol in Maude, which is a formal framework for analyzing concurrent systems. This distributed specification allows us to simulate in a realistic way the behavior of the protocol and provides a formal description besides the natural language description that is usually used. But we cannot prove properties with this distributed specification So what we did is to centralize, abstracting in a way the system, and then use mode LTL model checker. Well, actually we use real-time mode, so we do linear temporal logic model checking for time bounded. And well, with this version we can analyze properties on the protocol. So what's mode? Mode is a high-level language and high-performance system which supports equation and rewriting logic computation. So with equation you can specify terms that are equal, that usually are the data structures, and then you have rewrite rules that can express changes in systems. In mode it's usual to represent concurrent systems with multisets, which are called configurations, and are just objects and messages put together. Okay, so you can take some subsets here and specify regard rules to define how the system evolves. So, well, first of all, distributed specification in mode are built by using sockets, but it's not very realistic to have this high-level protocol and go to the details of the sockets to define the application. So we use a previous protocol that we specified some years ago, this enhanced interior getaway routing protocol, which provides messages of this form where underscores are placeholders. So you can write here the addressee, and here you can put your message, and it is given to the appropriate object. And it also provides a tick message from a Java server, so you can have real time. So this is the architecture we want to use. And well, I'm going to describe in some detail Kademlia, but not too much. So in Kademlia, both peers and files are just n-bit quantities, and well, you try to keep the files in the peers with an ID close to the file ID. Okay, and close means that we perform the byte-wise exclusive OR and just keep the result. A nice property of the algorithm is that it is logarithmic in the number of the lookup algorithm, is that it is logarithmic on the number of nodes. So, well, the contact information in the peers is the IP, the ID, and the port. And every node keeps lists of this information for all other peers, depending on the distance to them. Okay, so these lists are called K buckets, and each K bucket can only have K elements, where K is a parameter of the protocol. And well, these buckets are kept sorted by the time they were last seen. So the longer you haven't seen a peer, the closer to the head of the list. Are organized in a binary tree, which is called the routing table, but actually there are different implementation of this routing table, so it is also, the protocol is also parameterized by the routing table. Okay, so when a node receives any message, it updates the bucket. If this peer was already known, then it's put at the end of the list, so it's already seen by now. If it was not known, then if we have free space, it's also put at the end of the bucket, and otherwise the protocol asks the process at the head of the list. If it's already still up, then you keep it and discard the new one, and otherwise discard the head of the list and put the new one at the end. So this policy gives preference to old friends, which are supposed to be more reliable. So we have 4 RPC and its corresponding answers. Just ping that checks whether a node is up. A store that ask a node to store a file ID with the contact of the node storing it. Find node that just looks for a node ID, and find value that looks for a file. So how are we supposed to define this in mod? Well, this is a mod class where peer is the class name, and these are the attributes, these are the names, and then we have the types. So RT is the routing table, we have the files, the public files, the search files, an auxiliary list that keeps the information about the peers who are asking about the files we are searching for. And well, these are all the messages with all the answers. Pretty impressive. And I'm going to explain in detail the searching process. And just assume we have a peer, C48, and we have here, it's looking for file 12, and this is the timeout, and it has reached 0. So the next step will be to build a search list and then start looking for the file. So this is how regard rules are written in mod. We have the left-hand side here, where we say that we have a pattern here, the timeout of this file has reached 0, and we have the empty list for the search list. So we create, by using equations, the search list, and we will obtain something like this. Okay, so the three closest peers are 14, 16, and 0. So we need now another rule to start sending messages to these nodes asking for the file. And we have more constants, so the protocol is parameterized by a lot of constants and tables. The number of parallel messages that can be sent, and the number of peers we can wait for. Okay, so given the constraints are fulfilled, we can send a message of the form we saw before to this peer TR, which is the closest one. And once we apply this rule 3 times, we get the peer and the 3 messages that will be distributed by the underlying protocol to the corresponding peers. Okay, so once these messages reach the peer, we have 2 options. Just this peer knows the file, so it sends the information, or it doesn't know, so it sends a list with other peers that can have the file. In this case, this rule models the first behavior, so this peer knows about this file, so it sends this message find value reply to with the information about the file. And once this new message reaches the initial peer, we are done. So we leave in the configuration this file found message, so we can later prove properties on the configuration, and the searching process is finished. Okay, and regarding time, we have this tick message from the Java server, and we just have a delta function that updates all the times in a peer. Okay, so right now we can prove nothing. Okay, we just have a distributed specification. It behaves as we expected, but no properties can be proved. So to start trying to prove something, we use real-time mod, which is just an extension of mod, which eases the dealing with real-time. It provides this time and time inf sorts, which allow to represent the infinite time, and extra function that deal with this value And it also provides a global system sort, which just wraps the complete system to make sure that all the rules are applied at the top level. We are lucky because a system can be just a configuration, just like we had before. And this is the form of the main rule in real-time mode. Given a global system, it evolves by applying a delta function in time t, where t is computed from this function here, which is the maximum time that can be elapsed and no critical actions occur. Okay, so we have this real-time mode and we have configuration, but we need to put all configuration together so we can prove properties. And to do this, we need to abstract in some way the physical architecture. So we have a logical architecture that mimics this behavior. So we define our own processes that just keep in this attribute what we have in a local configuration. And we also have an object for defining sockets. Okay, so our logical sockets have two sides, some delay and two leaves for the messages for the side A and the messages to the side B, and just two rules to introduce messages and another two rules to extract messages from the socket. Okay, and we also need to reproduce connection and disconnections. So we add these live and reconnect attributes that can take the infinite value. So when reconnect is infinite, the socket is working, and otherwise it's not working, and it cannot move messages from one process to another. Well, in this way we have our system, but what we thought is that possibly not for proving properties on this protocol, it's not necessary to faithfully reproduce the behavior of the architecture, since there's probably not interest in disconnection for some properties or in sockets for some others. So we have a second abstraction where we work just with a multi-set of objects and messages all put together, which improves model checking and makes the configuration easier to understand. Well, we have other formal abstractions that you probably know, like partial order reduction and so on, but we're not going into details here. So, okay, now we can execute Kademlia in a centralized specification and check properties on it. So to execute, we have time rewrite and time first rewrite. We have the command find earliest and find latest, and time search. For proving properties, we have also time search and bounded time model checking. So, for example, a known property is the node insertion attack, or just a node pretends to have a file and it tries to fake the peer trying to reach this file. We can ask ourselves whether it is possible for this bogus peer to send us the information before the real peer sends us the information. So we could use this find earliest command just to check whether the first message resides from the attacker or from the real peer, depending on the parameters of the configuration. This will be a problem or not. And regarding model checking, we can prove some simple properties. For example, we have this property here. If a file is published and someone is searching for it, then it's eventually found. So we can define properties asking whether a file is published, is searched, or is found. We can use model checking in our initial configuration, saying that if a file is published and we are searching for it, then eventually it's found, which is true. Another basic property is that once a file is published, it will remain published until the publisher is disconnected, which just can be proved with this command. Well, I talk quite fast. So the conclusions are just we have a distributed specification of Kademlia that formalizes the protocol, and a centralized specification that allows us to simulate the protocol and to check properties on it. But we have a lot of work ahead. For example, we would like to improve the way we deal with time. We just add one or subtract one, we get a tick message, but this is not very realistic. We would also like to use the narrowing techniques that we have now in mod to prove better properties. And it will be also interesting to check to compare the performance of the protocol when you vary the parameters. So you can take different routing tables and different case, different limits, and check how the protocol varies. Finally, we will also like to study more complex properties. That's pretty much all. Thank you very much.
Thank you again. Is there any question?
Can you try to tell us why you decided to use mod as opposed to, let's say, spin?
Well, the most honest answer is that I'm very used to using mod, being programming in mod for many years, and then kind of expert programming in mod. So that's the simplest way.
But if you really have temporal properties, wouldn't be, and especially since you have to give it a time bound to see, does it happen in 20, does it happen in 30, does it happen in 40? It wouldn't be more natural to have a full-fledged model checker where you can just say eventually?
Well, we have a real model checker without time bound, but there are no finite number of states, so we cannot use it.
So why is the number of states infinite here? What makes it infinite state?
Because the time, messages have time and it's added up, so you need to abstract it.
So you need to explicitly model the timestamp of the messages?
Yes.
I see.
Thank you. So I think there are several questions. I think we have room for maybe one or two more.
Yes, after the question why this tool, now the question why the subject, why Kademlia? So you mentioned this property, you want to check if no one can give you back false information, but that would be irrelevant if the information will be signed. Or yes, why Kademlia? Why not something similar?
Well,
which doesn't have these issues.
Sorry. So we decided to analyze Kademlia because it's widely used. So, well, when we analyze protocols, well, it's interesting to have some challenges, but it's also interesting to have a real protocol that is being used. And in fact, you can, with this, I think it's interesting this find earliest because you can simulate with your real network what's happening here, and then why is this attack working or it's not working, because maybe it's because of this socket that it's too slow or whatever. So I think it's interesting to have real protocols and try to check real properties.
Okay, so you can validate it. But would you also be interested in doing CJDNS, for example, which has a similar mechanism for routing, only the IDs come from public key and cannot be forged? Or maybe the GNU-net DHT?
Well, we haven't think about it yet, but probably it will be interesting.
Okay.
Any last question for Romano?
If I understand what you said, you described Kademlia in the first part of your talk, and then you say that in order to do some verification, you have an abstraction of it, and you do this verification on the abstraction. So is that all right?
Yes.
Yeah. So now, how do you prove, or how do you are you sure that this abstraction is indeed an abstraction of Kademlia?
Well, it's not really what probably I didn't explain it properly. It's not an abstraction of Kademlia, but an abstraction of the sockets by mod. So Kademlia is just formalized, and what we are abstracting to prove things is just putting all them together. So we are abstracting different computers in just one. So we are just abstracting processes, but not anything about Kademlia.
So, yeah, but you are abstracting something.
Yeah.
So, how are you sure that the abstraction you have made is indeed an abstraction of the thing you abstract?
Yeah. We didn't really prove anything, so it's just faith.
Okay. Thank you.
So let's thank our speaker again. So this is goodbye for today, I guess. Thanks a lot to all of you.
Actually, it's really nice. I should have used that example. It's much more.
Che ti sei?